Right, so we'll start today by doing a few simple numericals concerning current and charge and all of that, and putting these equations that we learned yesterday to good use. So let's take a look at this. Right, we learned that electric current is charge passing a point per unit time. Right, so that's I, which is current, or equals to Q over T, which is charge over time. And the current is given in amperes, the charge is given in coulombs, and T is given as seconds, right? And if we move that around, we get Q equals to I into T. So, right, Q equals to I into T, that's nothing new. Just move this around and you get that. So, right, it's over here as well. So that is how the charge or the coulomb is defined. It is, right, the charge passing at any point in a circuit when a steady current is flows for 1 second. So let's put that into use practice. Let's apply that. So we have a question. It's a very simple question, obviously, but we have a charge of 2 coulombs. So here's a question. Charge of 2 coulombs passes a point in a circuit in 5 seconds. Right? What is the current? And so we know I equals to Q over T. So what is this going to be, Sobia?
Wait, 2 or 5?
Yes. Right, 2 coulombs per 5 seconds, which is going to give me how much?
Just a second. 0.4 if I'm not wrong.
Yes, it's going to give me 0.4 amperes. Okay, then we have another question where it says there's a current of 3 amperes, so I equals to 3 amperes, and it flows past another point in the circuit in 10 seconds. So time is 10 seconds, and asking what is the charge. So what is the equation we're going to use?
Q equals to I multiplied by T.
Good. So Q equals to I multiplied by T, which will give me 3 into
30.
10, which is 30 what?
A amplitudes. No, wait. Q.
Q, what does Q represent? What is Q?
I think that was for current. No, the current is. Let's see. I forgot how we pronounce that.
Charge.
Yeah.
Q is for charge and it is given with coulombs.
It is what?
Coulomb,
Coulomb. Okay, got that.
capital C.
Okay.
Right now, obviously, very basic questions, but just putting that, what we learned into a bit of practice. So there are two more questions, right? It says you got a current of 2 amperes, I equals to 2 amperes, and it flows for 20 seconds. So T equals to 20 seconds. And again, they're asking you how much charge passes. So what is Q? And so again, I'm right, Q equals to I into T. So what would it be, Sobia?
It will be 2 multiplied by 20.
Which will give me what?
40.
40 what?
Column.
Coulomb.
Coulomb, yeah.
There's another question.
Let me guess, I have to do that one as well.
Obviously.
Oh, why not her?
Oh, she's not at the desk at the moment. Right. You have a charge of 3 coulombs. right? And it is passing through a circuit for 7 seconds. And so what is the current? And so what's the equation we'll be using?
Uh, I equals to T multiplied by Q.
Heh?
No, wait. Q over T, sorry.
Yes. And so that would give me what? What are the
Wait.
values?
That would be 0.42.
No, first give me the values. What's Q?
Q is the charge.
What is the value given in the question?
3 over
3.
T.
And
Over, sorry, 7.
yes, and that would be
0.42 C.
no, it's current. What's current?
I.
No,
Wait.
I is the symbol for current. What's the SI unit for current?
E.
A for ampere.
Yeah.
Okay, so these were some questions regarding the ampere and the coulomb, right? Now let's move on and talk about the other thing we did yesterday, which was potential difference and electromotive force. So let's first take a look at the equations for that. So, right, we had, right, E, which is the electromotive force.
I think this is depends on what the subject is. We're just moving around with the symbols, right?
Yeah, so you just focus on one of them, right? So E, which is electromotive force, equals to W over Q, which is work done divided by charge, right? So if W joules is the energy transferred or work done when charge Q is moved around, a complete circuit, then it is, right, joules per coulomb, right, as given over here.
Q is the charge, right?
Q is charge, W is work done or energy transferred, which is given in joules.
Okay.
Right, so EMF, electromotive force, or E, is given as joules per coulomb, right?
Okay.
Joules per coulomb. And the potential difference is pretty much the same thing. The only difference is that it is when, one coulomb passes from one point to the other, uh, between 2 points of a circuit, right? 1 volt is when 1 joule of energy is transferred when 1 coulomb passes from one point. So it is across some component. It is not the entire circuit. EMF is for the entire circuit.
V stands for volts.
Yes. Right? So V, voltage, actually. This capital V over here stands for voltage, which is another term used for potential difference.
Isn't E for volts?
No, this is it's given as volts, yes, right? There's a difference between volt
And
and
voltage?
yes, right? Volt is the joules per coulomb thing we talked about. So that is called the volt, right? Voltage is a term used for potential difference. So you got EMF and you've got voltage, right? Both of these are given as volts, which is joules per coulomb. Okay.
Okay.
Now, how did we get this? Similar to, it's exactly the same equation. It is work done per unit charge. You move that about, right? And you get V into Q, which is voltage multiplied by charge will give you the work done. And you substitute the equation for charge with I multiplied by T, and you get work done is VIT, right?
Oh, that's a lot.
Yeah.
Okay.
So let's put that to use. So the question is asking us, right? A lamp is connected to a battery in a circuit and a current flows. So they're asking us to calculate the potential difference when 6 joules of work, so work equals to, here's a question, 6 joules of work is done when 2 coulombs of charge passes through the lamp. So the charge is 2 coulombs and they're asking you for the potential difference. So what is the equation for potential difference?
V equals to W divided by Q.
Yes, right. And so you're going to do V equals to W over Q, which is what now? What are the values of W and Q?
W is 6 and Q is 2.
And so that's going to give me a voltage of
3.
3
Joules per
volts.
coulomb.
Joules per coulomb or volts,
Oh, sorry. Yeah.
right? Here's another question.
Which Haram will do?
She just did this one.
Well, I did 3 others.
So again, they're asking you to calculate the potential difference. No, wait. They're giving you the potential. So the potential difference is 5 volts. And they're asking you to calculate the energy transferred when a current of 2 amperes, so I equals to 2 amperes, and time is 5 seconds. And they're asking you for energy, or in this case, work done. Right? So what's the work done? So what equation are we going to use over here?
VIT.
W equals to V multiplied by I multiplied by T.
Yes. Right? So the way they've given, let's first solve this. So V I T, right? And so that would be 5 into 2 into 5, which will give me how much now?
50
50 what?
joules.
Joules. Good. Right? Remember that VI is Q. Sorry,
Yeah.
not VI. My bad. IT. Right? IT is joules. Q. So what they did in the book is first they calculated Q equals to IT equals to 5 into 2 equals to 10, and then W equals to V into Q equals to 10 into 5 equals to 50 joules. So that it's the same thing. Okay.
Yeah.
Like what does I stands for?
Current.
Q is also current.
Q is charge.
Okay.
Another question. They're asking you the potential difference across a lamp and electric circuit when the work done is 8 joules. So work is 8 joules, right? And the charge is 4 coulombs. And they're asking you for the potential difference. So again, what are we? What equation are we using?
V equals to W over Q,
Yeah.
which will give us 8 over 4, and the answer will be 2 volts.
Yeah. So this is pretty basic, isn't it?
Yeah.
Right. Okay. So let's move on. Now that you've done a few practice questions, just to sort of.
More questions?
Oh no, we're moving on to the next topic.
Okay.
And the next topic is Unit 4.2.4, resistance. So to make life simple, remember when we were talking about motion, we mentioned friction.
Yeah.
What is friction? Do you recall?
When
Or
when
drag? What is drag? Friction is a kind of drag.
when two surfaces rub against each other,
Yeah, so what happens?
they create friction.
Yes, but what does friction do?
And less difficulty to move. Or like,
Difficulty to move, right? So friction opposes motion. It goes against movement,
Yeah.
right? That's basically what resistance is. Now, this is not the scientific definition, so I don't want to. You shouldn't be using this in papers, but right, it's sort of the friction of electric circuits. Right, it is the opposition to the movement of current, which means the flow of electrons through a substance. Right, and obviously when we're talking about substance, we're talking about some sort of conductor, because we're not talking about insulators. Insulators do not allow electricity to pass through anyway. So, right, when we talk about resistance, we talk about some form of conductor which will allow electricity to flow through. The question is, how easily will it allow electricity to flow through? Right. So just like with friction, the lower the resistance, right, the higher the current. Right. Okay. V equals to IR, and so I equals to V upon R, and so the low, yeah. So the higher the current, which is the flow of electrons, right? And obviously, the higher the resistance, right, the
The higher the
the lower the current. So, right, current and resistance are inversely proportional.
resistance and friction are the same thing.
No, no, it's I just used friction to explain
Okay.
what resistance is. Resistance and friction are not the same thing. Just like friction goes against the movement of a body on a surface or through air or something, right? I mean, in air
Yeah.
it's called air resistance, but point is that it opposes motion. Similarly, in these conductors, right, some allow electrons to pass through them much more easily as compared to others. Okay,
Okay.
and so the ones that allow electrons to flow through them, which means for current to flow through them much more easily, have low resistance as compared to the ones that have high resistance, so they sort of block the flow of current. It is flowing, but with more difficulty. Okay.
Yes.
So a good conductor has low resistance, and obviously a poor conductor has high resistance. Right. This brings us
uh,
to, yeah. Go
sir,
ahead.
I have a question.
Yeah.
Um, so resistance is just directly blocking the other thing, while friction just rubs against each other until it slows down and
Okay.
stops it.
Okay. Again, right? The two are not related,
Yeah,
right? Ha. Friction is when two bodies physically, move over one another,
until the other thing just stops or slows down.
unless there's an unbalanced force and resultant force and all of that.
Yeah,
Resistance is how easily electrons can flow through a material. If they can flow through easily, that means resistance is low. If they're not flowing through easily, means resistance is high.
Okay.
Right? So how easily electrons are able to flow through a material is the resistance.
Yeah. Okay.
Again, do not confuse it with I did not mention friction to say resistance is friction.
No. Yeah. No. No.
Okay, so please don't confuse the two.
No. Okay.
Okay, so if the current of a conductor, right, I mean the relationship between resistance, voltage, I scribbled that over here, but the relation sorry, the relationship between the three is resistance equals to, right, voltage per unit current. Okay.
Okay.
Which things are good conductor of resistance?
Hmm. Hmm?
Like what are good conductors of resistance?
Good conductors, like you do not conduct, but conductors have resistance.
Oh, okay.
Conductors have resistance, right? If they have low resistance, that would make them good conductors. If they have high resistance, that would make them poor conductors.
Okay.
For example, silver is a very good conductor of electricity. That means it has low resistance, right? The reason silver is not used is because it's expensive, right? And so the next best thing you have is copper. And that is why copper is used in electrical wires and everything, because its resistance is reasonably low. Okay.
Okay.
So this tells us that when you have a certain potential difference across a component in the circuit, the smaller the value of current, the greater the resistance will be. And obviously, the higher the value of current, the lower the resistance will be, right? Because the potential difference is, it is the value of the component, how much work is being done per charge. Yeah. So it depends on, right, the current being supplied. Now, what resistance does, if there's high resistance, for example, it's going to produce, right, heat, among other things, right? And this is actually put to use. For example, now, I don't know if you ever seen those filament bulbs, right? Those old bulbs that had like a wire going through them, they were made of glass,
Yeah.
right?
Yeah.
And so, right, when they would become hot, right, the resistance would increase and that would make the bulb hot. And so when the bulb was on for some period of time, you couldn't hold it in your hand because it was like super hot, right? And that was because of the resistance. And so we're going to talk about, I don't want to, like, may make like a mess about this, right? Resistance is also sort of related to the temperature. Sometimes in some materials, the higher the temperature is, the higher the resistance is. In some, it's the other way around, right? Resistance decreases with temperature. So it really depends on the material. But over here, let's just focus on the basic concept of resistance. All right, so resistance is the current applied across a component having a certain voltage, right? If more current is applied, resistance will be low. If less current is applied, resistance will be. And obviously, right, you can move this equation around. So let me just remove that. And you can get, for example, V equals to IR, or I equals to V upon R. So, right, you remember one and you can get all the others, right? It is, resistance is given as ohms. So R is given as ohms, and the symbol for that is the Greek alphabet omega. You don't need to remember what this is called, you just need to know how to make it. Okay? So resistance,
Yeah.
the SI unit for resistance are ohms, and they're given by the symbol omega. Okay? So for
Yes.
example, if you have a uh, current of 2 amperes and you have a voltage of 12 volts, what's your resistance going to be?
Uh, we will do 12 over 2, right?
Yeah, this will give me 6
Yeah.
ohms.
So many. Oh,
Okay,
Yeah.
so the ohm is the resistance of a conductor. In which the current is 1 ampere when a voltage of 1 volt is applied across it. Okay,
Yes.
so we did one. Let's do a question on the go. And so you have a current of 0.5 amperes flowing through a resistance of 5 ohms. What is the voltage?
we will divide 5 by 0.5 now.
No. Look at the equation.
We will multiply.
Hmm. So V equals to IR equals to 0.5 times 5 is giving me 2.5 volts.
Yes.
Another question. Right? The potential difference is 12 volts. And the resistance is 24 ohms. Right? What is the current? What's the equation we'll be using?
R equals to V over I.
Right. Which will give me what?
Current
So what are the values I'll be using?
12 over
potential
24.
E
Which will give me how much?
0.2.
Eh?
0.5.
Nice. And
And the interesting thing is in both these questions, the current is the same, right? The resistance and voltage is different,
Yeah.
right? Obviously, I didn't plan that, but interesting. Another question. Uh, right, you have a current of 0.30 amperes and a potential difference of 4.5 volts. What is the resistance?
R equals to V over I.
Yeah,
That will be 4.5 divided by 0.30.
which will give me how much?
Uh, 15.
Ohms.
Yeah.
Okay.
Yeah.
All right, we have time.
Can we do another question?
Oh, you're having fun?
Yeah.
Okay. So we have a current of 0.2 amperes and the resistance is 10 ohms. What is the voltage or the potential difference?
We will multiply 0.2 multiply by 10.
Which will give me how much?
2.
2 volts.
Yeah.
Okay. Next up are resistors. Right, so these are electric components that provide resistance. Okay. Obviously,
Yeah.
they are made of some form of conductor, right? It could be wires, it could be carbon, something. And they have many applications. For example, in your TV, right? Or anywhere where you have a volume setting, right? When you decrease the volume, what's happening is the resistance is increasing, right? And so there's lesser current flowing through, and so the volume decreases, the sound decreases. Whereas if you increase the volume, the resistance decreases, there's more current flowing through, and so more energy is being transferred, more electrical energy is being transferred, and so you get a higher volume. Interesting, huh? And so electric energy is converted to sound energy. And so resistors can be from a few ohms to millions of ohms, depending on what application they're being used in. So you have fixed resistors that obviously have a fixed value, and then you have variable resistors in which the value can be changed. What value? Value of what?
Resistance.
Yes, resistance, right? We're talking about resistance. So they're also called potentiometers. Since it's mentioned in the book, I'm putting it here. Could come up. So, right, what happens over here is, right, the potential difference is the same, right? By sliding, like by changing the resistance, you're basically changing the current flowing through. Okay.
Yeah.
It could also work a different way. So there are two types of variable resistors, right? One is called the rheostat, and what this does is it changes the current flowing through. And as you know, as R equals to V over I, right? Then,
Yeah.
right, the lower the value of current, the higher the resistance, and vice versa, right? The other type of variable resistor is called the potential divider. And this changes the value of the voltage. This changes the potential difference uh, applied to a device. Right, so basically the potential difference across 2 points of a circuit. So there are two ways resistance can be used, right? And so again, right, so R equals to V over I. And so if you decrease voltage, right, you're increasing resistance. Sorry,
Okay.
my bad.
I think the
No, no,
resistance decreases.
no, it's directly proportional. So if you increase the voltage, you increase resistance. If you decrease voltage, you decrease the resistance as well. Okay. Hello.
Yeah.
Yes.
Can I
Okay.
ask something?
Yeah. Question.
Yeah.
Uh,
What's the difference between current and volts?
current and
Volt.
current and volt. We need to go back for that. You got confused just now.
Yeah.
And so current is the charge passing a point per unit time. That is current.
Okay.
Whereas voltage, right, is the energy transferred or the work done when a charge moves around the circuit or across 2 points.
Okay. Thank you.
Okay.
Yes.
Now, just to show you from the book, right, the way they are drawn in a circuit. Let me put that up. So this is a variable resistor. This is what it looks like. And so you can see this is a coil of wire. They're terminals, right, for the circuit. So it's going through. And this is sliding contact, right? The shorter the distance, the lesser the resistance. The greater the distance, the more the resistance, right? And so it's used in, for example, to control the volume or other things, or the thermostat of a heater, for example, right? In that case, I mean, it has various applications, and so it can be used in two ways. The rheostat. So this is what the rheostat looks like, right? A general, like the thing is we need to know these, how to make these components in a circuit diagram. So if I just go back, uh, this is this circle with a cross is what a bulb looks like, a lamp looks like.
Yeah.
The short line and long line is what the power source or battery looks like. The short line is the negative terminal and the long line is the positive terminal.
Yeah.
Right, so you can see over here, right, the long line is the positive terminal, the short line, the circle with the A in it is the ammeter. You got a lamp over here, and what else was it? Alternating current. Yeah. So the symbol for alternating current in a circuit is this thing over here with this, right, wave type pattern in between. And so in case of resistance, I should zoom out. Yeah. So a resistor is like a rectangle with an R labeled over it. It's a rectangular box, right? So that's a resistor, right? Or in fact, just a rectangular box. That's what a resistor is, how it's shown in a circuit. A variable resistor is shown as a rectangular box with a diagonal arrow pointing upward from left to right. But more specifically, if you're talking about a rheostat in which the current can be changed, this is what it looks like. So a rectangular box, and they have this arrow, pointing in the middle of it, which shows that the current can be changed. Whereas for a potential divider where the voltage can be changed using resistance, uh, right, it's a rectangular box with an arrow with a circle. Okay. So they do have, I believe, a glossary of all these symbols. Uh,
Okay.
why do I recall it was there at the end of the book?
Are you looking for the glossary? It's right there above. Yeah.
No, no, no.
Okay.
They had like a list of the electrical symbols. I don't know.
I think it was in another book.
Yeah, I could be mixing it up. Maybe I'm recalling it from somewhere else. Anyway, right? So those were the way they're drawn. Okay.
Yes.
Okay.
Do we have time?
Yeah, 15 minutes.
Okay. So let me just go back to the whiteboard. Just give me a sec. Sorry. Okay, so I'm going to leave Ohm's law. The only thing I'm going to talk about is, right, resistance of a metal wire very quickly. So when we talk that conductors have resistance, then metal wires, which are conductors, also have resistance. And so what we need to know is how, right, resistance is affected in a metal wire. So the resistance of a metal wire depends on three things. First of all, it depends on the material itself. Right? For example, silver, copper, aluminum, whatever it is. The second, it depends on the length. Right, so the resistance increases with length. And the third is the cross-sectional area. Right, so the resistance increases as the cross-sectional area decreases. Right, basically meaning that the thinner the wire is, the more resistance it will have. The thicker the wire is, the less resistance it will have. Does that make sense?
Yes,
Why does it make sense? Why will a thicker wire have less resistance as compared
because
to
it's thick.
a...
It does not. It resists more.
No,
Because like less current will pass through.
a thicker wire has lesser resistance. Does that make
Because
sense?
like yeah,
How does that make sense?
because like less current will pass through it.
No, you've
Like
got
because it has more electricity.
okay. Let's put it this way. You've got two pipes.
No, wait. I think the thicker wire should resist more.
It doesn't resist more. It has less resistance, right? For example, these are two pipes from which water is going to flow. Which one is going to allow more water to flow?
The thicker one.
Exactly. Same thing for electricity. When the cross-sectional area is greater, right, there's more space for electrons to flow as compared to the thin one.
So there is, which causes it to resist more
Yes,
than the thicker one.
the thicker one has lesser resistance because there's more, space for the electrons to flow through.
So you're saying there is less resistance in the thicker one?
Yes, the resistance increases as the cross-sectional area decreases.
Like, but the thicker one would have like more resistance, no?
No, it doesn't.
I think we it will take us a moment to wrap our head around that.
Right, so this is called resistivity. Right, and it shows that the length of the wire or of the material is the resistance is directly proportional to the resistance, or let me just put it this way: resistance is directly proportional to the length. Right, but resistance is inversely proportional to the area, right? Which means if you double the area, right, you end up halving the resistance. The more the area, the thicker the wire, the lesser the resistance.
Yeah. Okay.
Okay, what you're thinking is it's thicker, so there's more area for it to resist. And that's why I give you the example of a thin pipe and a thick pipe. I mean, a pipe with a narrow lumen and a pipe with a thicker lumen. A wider lumen, so not thicker lumen, a wider lumen, right? And so the one with the wider lumen is going to allow more water to flow through. And similarly, right, a thicker wire with more cross-sectional areas are going to allow more electrons to flow through as compared to a thinner wire, right?
Yeah.
Okay, I'll stop here for today, right? There's just the Ohm's law left, which is not a lot, but still. So we'll cover that the next time, and then we'll be done with this chapter.
Okay.
Uh, there are some numericals, I guess, to do. which we can do next time as well after a quick review. And then we'll talk about electrical work and yeah, just make our way forward. In fact, we're almost done with unit 4.2. So just electrical work is left, and then we'll move on to unit 4.3. And yeah, okay, here we are, right? This is where the circuit symbols are given.
Okay.
It's in unit 4.3, and I saw it somewhere.
Oh, okay.
Yeah, so it is there. I just wasn't looking in the right place. Anyway, all right. So see you guys next time.
Okay.
All right.
Allah Hafiz.
Allah Hafiz.
Uh,